I do realize that people are doing design projects, and it's week 11 of semester, so I'm not sure what I was thinking when I decided to volunteer for week 11, but it seemed like a great idea at the time. So what I will talk about is looking at powering robots and really looking at batteries specifically. So I do a lot of work with electrochemical systems, so electrochemical energy systems, and so robots, of course, is just a massive subgroup of that. So I kind of went into looking at, what are they using them for robots, and then I'll talk a little bit about what we actually do with the design for the batteries as well, and what kind of flexibility we have around design for the batteries that we're using in the robots. Yeah, so anyway, if we look at the robots, then the things that we're kind of interested in, we're interested in power autonomy. So often, if you want to have an autonomous vehicle, you're going to need it to be having autonomous power as well. So this often means that you're actually using it with diesel powered, so it could be a combustion engine, so that's fine. You could use that, but with us trying to go greener, then they're trying to look at more sustainable ways to have autonomous power on vehicles or on whatever they've got. So you've got robots, you've got your drones, and autonomous systems. And so trying to actually look at how can we get power autonomy. There's a lot of work. When we look at batteries, there's a lot of work on lightweighting of the batteries. So how can we make them as light as they practically can be and as compact? I kind of think that light and compact is probably pretty similar, but we need to make them lightweight and they need to be compact. Sustainability, of course, we don't want to have them running on combustion engines because it's going to be outgassing. So can we do it with batteries instead? And that would be also good for renewable. And a lot of design that we have, and I can see a lot of where the robotics is going as well, is in regards to wearable components. And so how can we get flexible batteries that we can use in wearable components as well? So there's a lot of design challenges if we look at the batteries for robots. So if I look at super large robots, I call these super large robots, and so there's a lot of work done in the school around autonomous mining vehicles as well. And these are massive. So they've got a payload of 360 ton, right? This is a huge payload that you're carrying on there. And of course, they're autonomous. And so that's going to make it a lot cheaper for people to be running these kind of systems. If anyone also has a question at any point, just ask, because I've compiled this thinking, oh, this is kind of interesting. But if you think, oh, you would have a different question, just fire it out. That might make it more interactive. Victor, unless there's too many questions. And there's too many questions. And I'm like, man, I haven't even got to the third slide. Victor, what's...
Are there any times where you essentially have the opposite kind of design criteria, where you want your batteries to be as heavy as possible?
I mean, then you just buy a lead acid battery from JB Hi-Fi. So I haven't encountered that yet. But I did think that you don't want them to be, in some applications, you wouldn't want the structure to be too lightweight, right? Because that could create it, but typically everyone wants them to be lightweight. So that's because normally, if you think of I have calculated it before, I can't remember off the top of my head what the size of the battery is on this, but they're absolutely ginormous, right? So these ones are actually both diesel-based engines, but they've got an electric version of those ones as well, and so that means that they've got batteries running on it. And so if you think a standard Tesla has half a ton of batteries on it, and that's not a big vehicle, you could just imagine the amount of batteries that you would have on something like this. So it's absolutely massive. And so for them, when they're designing the batteries, they want to make sure that they're very, very lightweight. They don't want lead acid batteries on there, because otherwise they'll have some trailers on the back of that as well. So making sure that they're lightweight. So how do we power these kind of systems, which are huge? Also, safety is a massive concern there. If we're working in Australian conditions, then it's hot as well, so we need to make sure that the batteries are going to be safe, they're lightweight, and they're not going to explode. I guess safe and explode's probably the same thing. But on the one end of the scale, if we look at robotics, then that is the one end of the spectrum. Then if I look at the other end of the spectrum, this is the other end of the spectrum. So if we look at really, really small robots, then you've got these robo-bees. I don't know if this is commonly known about in robotics worlds, but there's robo-bees, which are really, really lightweight. Robots that were made by Harvard, I think they've made probably about they were designed about a decade ago. And so they're small, like they're 3 centimeters, they're really lightweight, they can actually land on water. But the thing is that they actually require tethering. So if I look at this here, you can't really see it. This is a classic, shot that you would get. Oh, here, there's a little tether that's in here. So that actually these are all tethered systems. And so to actually power them is that actually you need to be connected to power to actually run these kind of systems. But they've been really heavily designed, all really fancy materials that you're going to be using in there to make sure they're incredibly lightweight. Those wings are really, really light, and the body is light, and so they can do whatever they need to do. There are also these swarm robots as well, so they've got these kilobots. So these, you can see then the size of that kind of kilobot that you would have here is this kind of size. I guess this is some kind of American coin if someone knows what that is, but just a general idea of what that size is looking like. So if you're going to want to power this kind of system, you need a small battery within that system. And so you've got really complex spaces that you're designing batteries for in that kind of, in this system, the kilobot is really confined spaces. You can have complex environments that you're going to be working in as well, because some of the swarm robots, like where are they going to be going out to? What are the environments that they're going to be going out to? How can you continuously be powering them with battery power to actually get out? And how can you make sure that it's not going to get too expensive and it's not going to get too heavy as well? So with the Robo-Bee, you can see that there's not really much to work with there, right, in regards to mass. It's really, really light. They're very, very tiny. I don't actually know what the mass is. Maybe, Victor, you can Google the mass of a Robo-Bee. But I remember it was tiny when I looked at it. I can't remember what it was off the top of my head. But they're really small. So where do you put a battery if you're going to try and power that and power it autonomously, so without kind of tethered power that we would have that's there? So there's another thing that we look at is also when we look at powering drones. So of course, another area that we're really interested in is how can we power flight? And so for robots, then drones are important. I've also looked at powering aircraft as well. So, and those batteries are also big. So you have two ends of the spectrum when you're looking at powering. Does anyone work with drones? Does anyone work with drones? No, no. So this is definitely, anything that's flying is an extreme end of battery design because the energy density. Oh, you work at JCAR? Oh, that's fantastic. We could just get our lead acid battery directly from you then. Or maybe a lithium-ion battery. Which one do you work at? Enogra. Oh, that is way too far away. I go to the Wollongabba is my JCAR. Yeah. Pardon? Really? Are you serious? Oh my gosh, I didn't even see that. Normally I get called up to give some kind of comment about it. When did that happen? Oh. What's it? Really? Oh, they must have, but I've been there since then. Have they built it again? This feels like it's going off track. Wow. Oh, that's really dramatic. So obviously, the safe design of batteries is really important so they don't explode and burn down buildings. But actually, it's a massive issue, and I comment a lot on battery safety, and we have projects just on battery safety just to mitigate those kind of issues. So if we look at aerial vehicles as well, so you look at drones, so on the one end you have this battery vehicle, the battery drone that you have, and on the other end you also have fuel cells. I don't actually talk much about fuel cells here. I think I've got a comment on it later on, but you can see that also you can power them. Batteries might not be working out for you because you might be limited by how far it can go. I think it's got, if you have a look at the flight time, you've got about 35 minutes of flight time from a single charge from the top drone that you have here. But if you look at the drone, the Doosan, so that one's got 2 hours of flight time, and that one's powered by a hydrogen fuel cell system. So, but does anyone know what the catch is? Like, why would you not buy the Doosan over the Mavic Air 2? Size, yeah, actually. So the Doosan is massive. So the Doosan is a lot bigger, but there's also something about the Doosan. It'll be a compressed one. So it's phenomenally expensive. So the Doosan's like $100,000, whereas this top one, the Mavic Air 2, is $1,000. And so that's why, yes, you can get these amazing performance when you go into a fuel cell system because the energy density is even higher, but it's just supremely expensive to power anything with that. So when they've got these kind of systems, they're probably pretty specialist applications for surveillance, because who can afford to pay $100,000 if you could do surveillance with $1,000? Because you could buy quite a few of your Mavic Air 2s in comparison to the Doosan. Of course, this is a lot larger, right? That is, it's not completely apples for apples that we're comparing there, but it just gives you an idea that it is dramatically more expensive when you go for different kind of powering. And so maybe also the comment there is that batteries are pretty well-established technology. Some new powering technologies are less well-established, so hydrogen definitely falls into the less well-established technology. So I think the other thing that's interesting to do with your battery is that, okay, so you've got your battery, you can see that, for example, the drone, it could only go 34 minutes, which is not very long. So how can we do onboard charging? Because that would be another thing, that if you can couple it with some kind of onboard charging, then you could get it to go further. And so sometimes this feels like, when people talk about this, it feels a little bit like a perpetual machine, which seems a little bit not possible. So you need to be careful with what they are promising that they can do with these kind of systems. But one thing that you can do easily is you could couple it with solar panels. And so you have solar on top of your vehicle, and then it can be continuously charging your drone. You need to actually have the amount of area that you need to have for solar to actually do that is quite massive, but it could be something that you could use to offset it a little bit, just to get a little bit more distance from your system. So they actually have used it in the Mars rover, and I don't know if I've got it later on. I think I've got it in another slide where I will show you the updated version of the Mars rover. So this one uses solar panels, and it uses solar panels to then assist with getting additional charge onto your robot. But of course, you need to have sun for that to work. So there's this awesome idea, which is also, it's from Xiaomi, and it's called the Air Charge. And the Air Charge is this concept that you can actually charge it anywhere in the room. So you could have a device, you know, say we're doing, I don't know why I'm thinking of a robot vacuum cleaner, but just because of the image that you see there, have a robot vacuum cleaner, and you don't actually need it to be physically tethered to charge, but it actually just can get air charge. The massive issue that you have associated, well, any guesses on what maybe some issues might be associated with that?
Health concern?
Yeah, exactly, health. Like, so the charging would be really, really complex. Any yet? It's supremely inefficient. So it looks really, really cool, but it's really inefficient, and there's health concerns associated with it. And so, but I like the glossy image that they've got, right? They've done that quite well. But I just don't, some of those things just don't work very well. So that I would say is really far off. They also have this energy sharing that you have for your swarm robots. So the swarm robots, they can actually talk to each other. They would know if they've got more or less charge, and they can share charge between it in those kind of swarm robot applications. Actually, what kind of robots do people have favorite robots in the room?
Spot.
Pardon?
Spot.
Spot. Okay, so I'm going to need to find out what's that. What is Spot?
The Boston Dynamics.
Oh, the Boston Dynamics. Oh, you should tell me just Boston Dynamics. I know Boston Dynamics. But can the Boston Dynamics flip, or is that? No, it's not. There's another one that can flip. It's not I think the Cheetah. The Cheetah can flip, but I don't think the Boston Dynamics can flip.
They managed to kind of make it flip.
Did it flop? That's like my joke. That's my joke at like.
Flip over and
Yeah.
they kind of make it flop back over the other way.
Oh, okay, yeah. So Spot's your favorite. So is everyone's favorite the Spot? Is everyone's favorite?
Industrial robots.
Industrial robots.
Like welders, like robotic welders.
Yeah, actually, that is amazing.
They're like lifesavers.
Yeah. Well, I guess that it also means that you don't need to physically do that really dangerous work. And so I think that that's something that I think, like with these swarm robots as well, or any of these like small robots that are going out for surveillance, they can go into really, really nasty environments and go where you don't want to be going. So actually the applications are pretty amazing for, from a human perspective, in that we don't need to do that really dangerous work anymore, or if it's a really unsafe environment. So I know that they were thinking of using them also in earthquake zones as well. If you've got collapsed buildings, then you can get robots to go out into the collapsed buildings to try and find people within the collapsed building as well. I think it's pretty, the range of applications is just astronomical. I don't have an image of Spot in the slide. So everyone, don't get too excited. So anyway, so you've got all of these. So what I'm trying to say is that we've got supermassive robots, really small robots. You've got flying robots. You got ones that can possibly like do a little bit of onboard charging. From those ones, the one that's, see, I've got the cheetah though. So the one that makes the most sense on here though is that is the solar. That seems the most credible. Hello. Is your favorite robot Spot as well?
Oh, absolutely.
It is. Everyone likes Spot. It's like, who's Spot? That was just me that said, who's Spot? Energy harvesting. So the other thing that we can do is energy harvesting as well. And so with these robots, so for example, I suspect Spot can do it, but I'm not 100% sure. But Cheetah actually uses, when you have some impact loading that's in it, it can use the impact loading that you can get, and it can then regain that energy and then use that to go back into the battery as well. And so you've got, that one sounds a little bit more like a perpetual machine, where he's like, there's only going to be, because you have to actually provide the energy to move it, so there's only so much you're going to get back from the environment as well. So there is a limited amount that you're going to be harvesting in that kind of condition. But it's a really interesting design to think about actually how can we get that energy back into the system. And it's the same when you think of an electric vehicle, right? The thing that's amazing with an electric vehicle is it can actually harvest the energy that you've got during braking. It can harvest that and put it back into your battery system. So that's also using that kind of idea there as well. So I also noticed that NASA has also recently updated their rover. And so rather than going to batteries, they're just like, we're just going to go straight nuclear. And so they've actually got, actually the problem wasn't so much with the battery, the problem was more with the solar. And so I think they had inconsistency with the solar, even possibly that they had coverage issues with the solar, and so that they had they had power supply issues with their solar. And so they thought, you know what, we'll just go nuclear. That's going to be a lot easier. And so they actually have a nuclear device then on the Perseverance rover. And this is also, but they still actually have batteries on there as well. So it's still, because it can just provides a base load. So you use base load power from your nuclear, and then it provides it to the batteries, and then the batteries can charge whatever, and then they've got separate components that they're actually running themselves, rather than just using the base load power from your nuclear. So I thought that was interesting as well, is that it was a very, very silent change that was made within the, not a very silent, but I was looking at it and there's all these pictures with the ones with the solar panels, but actually I think now it's just nuclear, because it's a lot more, it's easier to work with. It's rather than dealing with your solar panels, especially when it's really, really remote as well. So now I'll just go more into, so those are kind of the general things that I've looked at for your batteries, for your robots. And now I'll just go more into actual batteries. And so this will be a bit more battery technical, but anyway, hopefully you learned something. So we've got primary and secondary batteries. Secondary batteries are rechargeable, primary batteries are not. Doesn't mean that primary batteries are bad, but it just means you can't recharge them. So they got some good applications, but they'll have limitations in it. Sometimes actually the performance can be really, really good. So think about the application you've got. If you think that you can use a primary battery, use a primary battery. They can, it sometimes can be a lot simpler, because when you make a secondary battery, you need to create all of the materials need to be able to charge and discharge, and it makes your design for materials a lot more complicated. So that's what a secondary, you're going to be charging and discharging. It can store and it can be a source for the energy. Typically it's a higher cost because of those design issues that you have. The materials are a lot more expensive. The electrolytes that we use are a lot more expensive. But we can get pretty high discharge rates, and we can get lots of different applications from here as well. So if I look at why lithium-ion batteries, so this is the hottest area at the moment, is lithium-ion batteries. So you look at, so this is a Ragone plot. We look at the power versus the energy density that we would have. So you can look, so you can see, for example, a supercapacitor can get really, really high power density. So it means it can discharge the energy that it's got in it incredibly quickly. So you might use it in a starter, and if you want to take off somewhere really, really fast, maybe you use a supercapacitor to give you really, really high power, but it's not going to get you very far, right? So you can see the energy density that you get here in this green plot is really, really low. On the flip side, you can see why we kind of like the lithium-ion batteries, because it's got the balance of the two. It can get pretty high power, but the energy density is way better. And so this means that we can go fast and we can kind of go far. There's a huge range of lithium-ion batteries, and so we can redesign the battery either to make it a high power system or we can make it a high energy system. But normally, if you make one of them, so if you want a high power, you normally compromise on your energy. So if you have a look here, so these guys here, which are your high power systems, they're not going to get you very far, right? Because you're only going to get 60 watt hours per kilogram here. Whereas your high energy density, you're just not going to get the charge out of it very fast. So what they typically do is they make your electrodes, which stores all your charge in it, they make them, to make them high energy, you make them super, super thick, and to even really, really, I mean, this is an exaggerated thick electrode, right? So these are normally hundreds of microns, not like whatever this is, tens of centimeters. So you make them really, really thick, and that means you have lots of capacity because there's lots of place to store your lithium ions in that electrode, right? But the problem is that to get those lithium ions out of all of that material is really difficult to do, and so you can't do it really, really fast. It takes a long time to do it. On the flip side, if you want to make a high power battery, what you can do, you can make it thick, but you take half of that material and you turn it into carbon, and the other half of the material is the material that stores the lithium, and it means that it can get the electrons to the surface really, really fast, do the reactions really fast on that surface, and get it out of there really fast. So you just don't have, and because now half your material is carbon and half of it is your active material that stores your lithium, it means that you've reduced your capacity dramatically. So it's a lot faster. I can discharge really, really fast, but it's just I've lost capacity there. And so for any application, depending on what you're doing, maybe not for a drone, I don't know what you're doing, you would choose the right application. So people that are trying to make rockets, they would use a high power system, right? It's not going to go very far. People making cars, like EVs, electric vehicles, typically want to have a high energy density for the system because they want it to go far. So you need to compromise it. And you can see all the other batteries in between there. So you can see our friend, the lead acid battery, which Victor's using to power. What were you going to power? You're going to power your autonomous mining truck from that. So you can see here it's a really, really massive difference that they would have from an energy density perspective. So maybe I already went on this a little bit and then I've backtracked a little bit because I already told about active material. But normally what we have for a battery, I know mechatronics engineers love electrons and ions, so I thought I would do both of those things here. Obviously, I did not make this animation. So what we have is we have a cathode material, we have an anode material. The cathode material can be made out of anything. Say a common one would be LFP, lithium iron phosphate. And so what we can see, I would try and pause it because it's actually, I kind of find this really difficult to follow this video. So I'm not sure who this video, am I going to be able to pause the video? Maybe I need to do it this way. Let's see if we can do it this way. Because otherwise I think it's too difficult to actually. So here, we're looking at discharging the battery. And so you can see that the electrons are coming out from here, and they're going to the external circuit, and they're coming into here. And at the same time, when we discharge it, then you've got your, I'm not going to be able to do that, just because I don't run a full screen. So your electrons are coming from your anode, they're coming out from your anode, and they're going to your cathode. And then the lithium ions that you have that were in the anode, in the graphite, they're going to come out of that graphite, and then they're going to move through the electrolyte, which is in this middle section here. They'll move through there, and they'll move into here, right? And so you can see it here. So that's the discharge process. So the electrons are leaving, and the lithium ions are going into our cathode, right? And now if we're going to go the charging process, then the opposite. The lithium ions are going to leave from our cathode and they're going to go into the graphite, and then the electrons are going to go from your cathode then over to your anode. So what I want to highlight is, that was like, oh yeah, don't worry everyone, it's okay. I totally know how to use PowerPoint. So what I wanted to highlight from here is the importance of the materials that we have here. So if you choose a material that's really, really average, it's not going to store any lithium ions in it. And so both for your anode and for your cathode. So we spend a lot of time designing these materials to make sure that they can store a lot of charge in it, because if they can't, you're not going to be going very far, and you're not going to be going very fast. What was I going to say from here as well? I cannot remember. So we call that active material that you have in there. And this process, so some incredibly smart people came up with this, and they possibly got a Nobel Prize around it. So I think that's also important to realize that actually the super cool lithium-ion battery that you have in your pocket in your phone, that it is really amazing that people got Nobel Prize associated with actually the design of it and the way that they do the intercalation, so the lithium ions come into the material and they get removed from the material. The way that they do that process and the way they design those materials, there was one Nobel Prize given to 3 people that did that kind of development. And so from that, they got the commercial lithium-ion batteries were actually developed in 1991. So this is quite a long time ago, but you can see just the enormity of that redesign that they've got for those materials is huge. Because initially what you would have is we have a reaction electrode. So that means that it forms a reaction with each other to do the electrode process, like a lead-acid battery. But to have this, where the lithium ions are just going into and then being removed from the material, was a really completely different design. Also, the benefit that we have is that we can run it at really, really high voltages. And because we can run a lithium-ion battery at high voltages, it means that you can get more energy from your system, which everyone likes, except for when it explodes. So if I look at a battery, so people say, oh, how good's this battery? And it's like, I don't know anything about that battery. So I normally need to know lots of things before I can say how good a battery is. So on the very, very basic level, we have the materials. So what I showed you before, it had graphite for the anode, it had LFP for the cathode. Those are our really, really basic materials. And that's going to define things like what's the capacity that you have in your system, and it's going to define things like what the voltage is that you're going to be working at. So you start from your basic materials. The next thing that you need to think about is the format that you have for your battery, right? So you could have it in, so these are new ones that they've made for lithium-ion systems. So you've got these 18650s, which I know that everyone can buy online now. You've got the 4680s as well. And that just tells you about the shape that you have for the system. So they can be in all different types of shape. You can have prismatic cells, you can have pouch cells, you can have, what's the other one I've forgotten? There's a massive classification. But anyway, so this is just telling me the shape that it's in. So it doesn't tell me anything about the chemistry. So sometimes people would ask me, because I'm supposed to know everything about batteries, they're like, Ruth, what's the AAA battery? And I was like, I don't know, because it's just a format, right? But I normally don't tell them that in a condescending way. I normally say, actually, I just don't have enough information. So the format of the battery doesn't tell you anything about how it's working. You don't know anything about the chemistry. That's a completely separate story. So it's important to keep those two quite separate. The materials and then the format. The next thing that we need to think about is how we're going to pack them, right? So when I get a battery in that particular format, that's one thing. But if I want to run on an autonomous mining vehicle on it, I'm going to need to have quite a few of those 18650 cells to actually run an autonomous mining vehicle. And so this is where things start to get a little bit interesting and things start to catch fire, because the confined space that you're designing in, you need to think about what's the battery I've got, what operating conditions is it going to be running in, how do I need to keep it cool, because all of those things are going to be massive factors. And this, for each step that we go from materials to format to packs, I lose my energy density. And so my theoretical energy density for my pure materials might be amazing. And everyone thinks, oh, this is going to be the best battery ever. But then I put it into a format, and I've got a little bit of steel in there, there's some aluminium in there, and then I reduce that energy density. And then I take it from that format, I put it into a pack, I run some cooling liquid into the system to keep them cool so they don't catch fire, and then I lose my energy density as well. So we need to be careful for each of those steps. We need to be mindful about what's happening. So when I design the basic materials, you can think of, for lithium-ion systems, you can think of 3 main categories: LFP, NCA, NMC. They're written here if you would like to know that for reference. And they just have different performance behaviors that you're going to get. So some of them will have really, really good thermal stability. Some of them will have really high efficiency. And some of them will be really, really good energy density. But you can see here, there's definitely an inverse correlation. So the ones that are high energy density, these guys, don't look so amazing from a safety perspective. So normally it's a bit of a balancing act. It's like, how am I going to get something that's going to be safe and going to give me good energy density at the same time? So that's just to give you some ideas about the materials that we have. So also when we put them into the battery, when we actually make the full system, we've taken our basic materials that we've got, like the LFP, the graphite, and we actually need to we make them into a slurry, which is just like a giant paste. And then I was just trying to think about how to describe it. It is a paste. I think everyone's familiar with a paste. So you mix some carbon, the active material, and then you deposit it onto something that looks like barbecue foil. And it actually really looks like barbecue foil. So this copper that we have there and the aluminium that we have there looks like giant barbecue foil, except for the copper one's a little bit more expensive than barbecue foil, and the purity is higher than pure barbecue foil. And so you get your slurry, you deposit it onto that, and then you dry it. And this is really important, the barbecue foil, because that's actually where you get your current collector coming in. But you can see what I mean in regards to energy density is that's going to immediately kill your energy density. So that's why they also use barbecue foil for it. So it's about 18 microns thick, the barbecue foil. So it's really, really thin, but you need to get it really, really thin over a large area. So that's that. So you've got these current collectors, aluminium current collector, copper current collector. We've got our paste, which we've deposited onto them. And then in between, we have a separator. And then you put them all together and you inject it with a liquid electrolyte to make sure it goes through the entire system. And that's what happens here. So we have electrodes, separators, electrolyte, and current collectors. So does anyone know what catches fire when a lithium-ion battery catches fire? What makes it go kaboom? What's a problem? Any ideas or no ideas? Yeah?
Is there something shorts between the two foils or something like that?
Yeah, so you can get shorting between the two, so you can have a thermal instability, and then you can get a short between the two foils. And if you get a short between the two foils, what happens is all of the energy from your battery, which is really high energy density, goes through that contact point that you have here, and you can get really rapid heating in that contact point. So imagine that normally your current would be distributed on this huge surface area, but if you have a single point where all of the current can go through, it's going to go through all of there, and then the electrolyte, which is typically flammable as well, is really, really great, and so it's a great combination. So you've got high voltage, you've got a lot of current going into a small area. So I kind of thought one time when I was describing it, it's like, feels like it might be a small bomb that you have that's there, because when it shorts, it's really high current density in a very small area. So it's problematic. And the thermal stability that you have for the different materials is actually really different. And so those before, yeah. Yep.
What can cause the thermal instability in the first place?
So you can get destabilization. So for example, you could get local destabilization if you just have imperfection, and you might just get a small little mound, say in one section. It's slightly closer. It might be gradual in that you might gradually get higher and higher current going through an imperfection in your electrodes. So you have current density distribution inhomogeneities in the system, and then it gets amplified over time. So that could be one thing. You can also get destabilization of your materials. So your materials can release oxygen from them, and they can locally heat when they do that, and it's an exothermic reaction that you can get in that process, and so it can create local heating zones, and so that's also a big cause of it to catch fire as well. So those are probably the two reasons why you do it, and that's why some of the materials are just more stable, because they don't have that thermal heating process as much as the other materials. Yeah. Yep.
So does that mean that if it's pierced, does it always like short and explode?
If it's pierced, if it's physically pierced, so I wouldn't recommend to do that. If it's
like some application, like for the military, you might have to like assess its robustness against
Yeah, oh, okay, so piercing can be quite bad. So it depends on the state of charge that you have it in. If you have it in a high state of charge, so basically fully charged, and you pierce it, I think that would be probably quite bad. And then it could explode. Because you've pierced it, the electrolyte can get out, the gases can get out. So it's possibly less, I don't know, I've never tried that. But actually, so there's a lot of safety testing that they do around it, and one of them is actually around the mechanical rigidity for it, and so how does it perform underneath extreme mechanical loadings as well, and to see how it performs. But I'm not sure with that piercing what would actually the exact failure mode be. But yeah, I'll get back to you on that one. How about I like get a student to try that out? We have there's confined chambers that we do that stuff in. Yeah. Yep.
Since it's thermal stability, would that mean if you had it pierced and then you had a bit of water that's like at a little bit of cool or warmer temperature, would that be more likely to cause issues then?
So water is often a problem as well because it can create HF gas in the system, so hydrofluoric gas in the system. So we typically try not to get moisture in the system, so moisture is bad. And so that's why moisture is bad, because actually we often have fluorine in the electrolyte system, and so the fluorines that you have in the electrolyte system can react with the water, and so you can form HF, so that's never good. But it would not, the piercing, still you probably have competing reactions occurring simultaneously when you would pierce it. And so I don't know the speed at which you would get HF forming, but I wouldn't want to be around the battery that I would be piercing. How about that? Any other questions about battery piercing? Oh, Victor.
On that line, so a lot of fire extinguishers are kind of dealt to be, or kind of designed to deal with the direct reaction of whatever's happening, so depositing on the battery itself. Oftentimes you're kind of covered. If you do have some sort of gas, does even most of the fire extinguishers even help with that? Like, is it creating some sort of coating?
So the recommendation from the fire services is don't touch and evacuate, because the gases that you can get are really nasty and super toxic, and we don't even know what all the gases would be because the electrolytes are pretty funky. And so the recommendation is to evacuate. Yeah. So I wouldn't try any fire extinguishers on it.
I'm never going to try it. Just also out of curiosity, does it make a difference? Because the key thing is not actually the fire, it's that gas.
Yeah, it is the gas. So I don't know which fire extinguisher you can use on them, but the recommendation that I've had from the fire safety department is just to evacuate. Yeah. Yeah. Is that another question? No, that was a head scratch. Okay, good. Explaining batteries are a lot more interesting than ones that actually work, right? Anyway, so I think so hopefully you understand basically what's in your phone, right? And so you're in your phone battery, you can understand that. Then we can take them, you've got them different formats, and then you can put them into cylindrical, so you can see here, that's a full pack that's been made. So you're taking various cylindrical cells and then putting it into a pack like that. That's a pouch cell configuration. Coin cell, you know what they look like. The pouch cell is a little bit more flexible that you're going to be using then as well. And that gives you slightly better energy density when you're making it in that configuration. Also something to remember is that we do not have lithium-ion battery manufacturing in Australia because actually it's an incredibly expensive factory to set up, and it's really precise. So I think, I don't know if we could say as extreme as silica chip manufacturing, but it is got a lot of steps into it, and cleanliness is incredibly important. So they have really massive dry rooms where you're making that in, and the reason why we do that is to make sure we don't get any moisture in there, because that can create the HF in your system and it can kill your battery incredibly fast. So so I would love to see manufacturing in Australia, but we just don't have it at the moment. So this is just what I would like to show is just here is this idea about losing energy density, because we know for robots energy density is incredibly important, but you can see that when we take a cell level energy density of 175 and I put it into most of the packs, then immediately I lose quite a lot of my energy density. So actually in the design, going from cell design to pack design, there's a lot of work that needs to be done to get that energy density as high as possible, because there's a huge loss just associated with that redesign. So you can see in the top right-hand side, that is the design that you have from the Tesla, which is using these cylindrical batteries in a pack format. But actually, the newest design and the hottest design that I think is available at the moment is from BYD. Build Your Dreams, isn't it? I think it's Build Your Dreams. And it's from the LFP prismatic system. And they've created what they call the blade design. And this is using a chemistry that typically is not very high energy density, but the way that they actually done this design for the system for their pack, like the final pack, is really unique. And so they can actually get a really high energy density, even though the materials that they're starting off with aren't that amazing. It's because the safety is actually really good in their starting materials for the BYD, as opposed to what you have for the Tesla. The Tesla materials are a lot less stable, and so they have to make sure that you've got cooling, all these other things happening in there, and so that's why this is a lot better. This is the smartest, most recent design that's available for packs. I'm going to jump over that, and this is just saying, you've got to be careful with how you, I'm just going to say this very fast. Be careful with how your battery is working. You need to know what your chemistry is, the temperature, your depth of discharge, and your C rates. Otherwise, you're going to kill your battery. So what's going to happen into the future? So people would like me to make, or people would like us to make really, really high energy density materials. Where we started off in the 1990s, so it was 80 watt hours per kilogram. Where we're at the moment is, where are we at the moment? I should know this off the top of my head. Around this, I don't think we're there. So we're around this 300. We're under 300 at the moment. So NCA was there 300 watt hours. So where are we going to go into the future? So that future is the solid state batteries, lithium-ion battery from Tesla, which is a new design, lithium sulfur batteries. The problem with all of these systems is that the TRL level, so the technology readiness level for all of these systems is around 4 or 2. It's pretty low. So they're not really, really high TRL. So you're not going to be able to go to JCar anytime soon and buy those batteries because they're just not manufactured. They're not commercial at the moment. So that is where things are moving in that direction. But it's important to realize that there is a limit to what we can get. So we can get, say, from 300 where we're at the moment, possibly to 500, but I think there's a little bit of fudge factor in there because those are TRL2 that you've got. So these are really low TRLs. So this is, I would say, aspirational to think of where we're going to be getting. So it's important when you think of the robot design to think, actually, yeah, there's a limitation to what you're going to be able to get from a battery. And this is where you're at commercially at the moment. So to think that you're going to be able to get to that, get higher than that is going to be very, very difficult to do. I won't go more into, I just wanted to see what else I've got here. So I would say the future applications that we've got, so there are future applications. You've got electric trucks, you've got electric aircraft. So Eviation has an electric passenger aircraft, and that's based on battery systems that we have there as well. And these all want high energy, often they want high power at the same time, but they need them to be safe, right? They need to have safe batteries. There's also companies that are looking at hydrogen power as well. So if we look at those autonomous vehicles mining vehicles that we started off with, that these ones are now going from battery power to potentially hydrogen fueled with a fuel cell system in there as well. I would imagine that they have a beautiful price tag associated with these fuel cell systems with them. But they typically, when you go to a hydrogen system, the idea is that you can go further on a single charge. That is the idea, but it comes with a really big price tag at the moment because the development is just the amount of demand for fuel cell systems, the amount of manufacturing for fuel cell systems is way lower than what we have for lithium-ion battery systems at the moment. So I'm just like navigating because I did pull these slides together and thinking like where we're going to go. So I think this is where I like ending up at. So we've spoken a lot about like the batteries. You have an idea of what's actually in the batteries. We know that we shouldn't pierce the batteries because they could explode or maybe not, I don't know. But I would say that there's a lot of areas where needs lots of development. And I think that in these kind of areas where it's got like these exoskeletons, is that this is a really interesting area for battery design as well, because as opposed to a vehicle where you can just chuck a bunch of batteries into there. Now with these exoskeletons, you're going to want them to be flexible. So how do you make a flexible exoskeleton that's going to be battery powered, because you're not going to want them to be tethered. And so that is a huge challenge. And so I've just got some examples here from Exobionics here, Guardian XO. So for Guardian XO is for really heavy lifting. The Exobionics is really trying for rehabilitation. But you're going to want those to be flexible devices. And so now there's an additional challenge for the battery. So we looked at all the packs that we looked at before was a cylindrical, prismatic cell. But how am I now going to make the battery to be flexible as well? So the thing when we have lithium-ion batteries, they need to be really well sealed. And if they're not really well sealed, then you can get water into them, which we know is going to create HF gas, but it also just doesn't like it very much. And so to create really lightweight packaging for flexible batteries is a really big challenge that we're working on at the moment. So in these kind of applications, because you want to have good energy density, but it needs to be comfortable for someone to be wearing. So maybe not so much in this application, but definitely in that application, we need to have that. So also there's these assistive robotics. So you can actually, so that one's an AI. This one's, it's got biosignals. I don't even know how they do it. I don't know if anyone else knows more about that. Does anyone know anything about the Cyberdyne? So it uses like, it actually taps in and it's got biosignals that it uses for movement assistance in it as well. So not only is it robotic, but it also is bioassisted as well. There's also these exosuits here, which I feel like is maybe not a good direction to be going in, is like the exosuit for walking. I was like, I don't know if we need an exosuit for walking to reduce fatigue. But it is, of course, this is useful. In rehabilitation, of course, it's useful. But I could see people just generally wearing an exosuit, right? They're just like, I'm always wearing my exosuit. But you can see here is that there's a battery pack there, but it's going to be uncomfortable. And so designing a battery pack that can, say, wrap around here, be completely flexible and really rechargeable and not too heavy, that is the next big design challenge that we have. Large scale, high energy density. So I would say that was a lot of talking. Future for batteries, we need to have high energy density. Everyone knows that one. But it's not that easy to do. So normally you compromise one with the other. Get high energy density, probably power's not going to be amazing. And we also know when we go high energy density, often they like to explode as well. People want to have fast charging technology. We didn't really touch on that so much. Also this onboard charging. How can we do better energy harvesting onboard charging to get more power into the system to run the battery for longer? Safety is really important. No one wants to have an exploding exosuit. I wouldn't want to have an exploding exosuit. If your exosuit feels like it's getting warm, take it off. That's not good. There's a lot of work in regards to manufacturing techniques. So there's 3D printed batteries that we have as well. So we've also looked at something for like bugs, like how do we get a battery on top of a bug? And so, well, because you can just help it move. And so, well, they were using it for swarm robots. And so they were asking me, can I get a battery onto that? I was like, oh, that would be really difficult to do. But yeah, 3D printing of those kind of batteries or other kind of smart ideas to manufacture really, really small batteries, I think is interesting. And also really small, interesting cavities, like the spaces that you have for the robots could be really bizarre. So it could actually benefit from 3D printing them to get them into these weird spaces. Lightweight and flexible, yes, so for our wearable robotics as well, that needs to be. And then just balancing high performance and affordability, right? So all of these sounds awesome, but normally if you have an awesome battery, it's normally going to be an awesome price tag associated with the awesome battery. And actually the last thing that I really thought about when I was pulling this all together as well, the one thing that I thought about was just about the efficiency of the design, right? So we talk a lot about how can we get more energy density from the battery, but actually there's a lot around the efficiency of the design of the robot. So I remember when I was reading on the Cheetah robot, it's really interesting the way that they've done the mechanical design for the system to actually make it really efficient in the way that it moves. means that actually for a smaller battery, you can go further, or I don't know. But anyway, more efficient design of the robot is also really beneficial. So because you can always put a larger and larger and larger battery onto the system, but if you can make it lightweight, you can make it lightweight system, you can make it more efficient movement that you've got within the system, then that's going to be offsetting your energy costs that you have with your systems as well. So that is all I have to say about robots. I don't know if that was useful, but that is everything. There's like a lot more, but hopefully it was a bit of an overview. There you go.